Hello everyone, this is Stephen He from Penn State University. I'm here to present our paper, If in a Crowdsourced Data Annotation Pipeline, a GPT-4. This work is in collaboration with Chieh-Yang Huang, Chien-Kuang Cornelia Ding, Shaurya Rohatgi, and Ting-Hao Kenneth Huang. This paper compares GPT-4 with a crowdsourced data annotation pipeline. After the emergence of large language models, and they have a really good performance on different tasks, people started to compare the capability of LLMs with crowdsourcing. Several studies had already conducted experiments that compared LLMs with online crowd workers on annotation tasks. However, these studies focused on merely individual crowd workers' ability, which is not practical in real life. For example, if we can imagine a crowdsourced pipeline is a machine, then each individual worker is a small component of that machine. While a language model is like a different machine, it is unfair for us to use the language model to compare to a single crowd worker, just like we are using a system against a single component. During a crowdsourcing process, in addition to the individual crowd worker's ability, there are many more factors that could contribute to the final results. Those factors can be interface designs, requesters quality monitoring, and label aggregation techniques. As crowdsourcing practitioners, we paid more attention to the entire crowdsourced pipeline performance instead of individual crowd workers. We would like to see how much we can push forward on the crowdsourced pipeline for the best performance. So in our experiment, we tested 2 different worker interfaces, used 3 different cleaning methods following data monitoring and collection, and applied 8 different label aggregation methods. We tried our best to conduct a comprehensive and ethical crowdsourced process on Amazon Mechanical Turk, MTurk, and used it to compare with GPT-4 on data annotation tasks. We wanted to know if we have a well-conducted crowdsourced pipeline, will it outperform GPT-4? In our study, we chose the CODA-19 label scheme, which categorizes sentence segments from paper abstracts into 5 research aspects: background, purpose, method, finding, and other. The reason we chose this task is because of its balanced difficulty. The task requires the crowd workers to read a scholarly article, making it more challenging than basic sentence labeling. And it is not too difficult like requiring domain knowledge. And MTurk workers have successfully completed the task before. The original CODA-19 dataset contains papers before April 2020, and these papers were extracted from COVID-19 Open Research Dataset, CORD-19. To avoid data contamination arising from overlaps between our test data and GPT's training data, we limited our study on papers that were published after GPT's last cutting-off date in September 2021 at that GPT version. So we only extracted paper from CORD-19 on 2022 publications or later. From the extracted paper, we sampled 200 papers for the main experiment. We also sampled another 200 papers for user interface development and prompt development. Previous studies suggested different worker interfaces can impact on workers' performance. To address this potential bias, we tested our task on 2 different user interfaces, Basic and Advanced Interface. The Basic interface was designed by one of the authors. He was not familiar with designing interfaces for MTurk tasks at that time. The Basic interface includes annotation instructions at the top of the interface. The annotation panel is positioned at the bottom. Workers begin by reviewing the entire abstract to gain an overview understanding. Then, they can navigate through individual text fragments using Next and Previous buttons, and they can select the most appropriate label for each fragment. Afterward, workers can review their annotation using Next and Previous buttons. Once the annotations are completed, workers can click Submit to submit the task. For the Advanced Worker Interface, we adopted CODA-19 interface. It was designed by our crowdsourcing expert, Dr. Huang. The Advanced Interface had several advanced features. We provided a time lock at the bottom to prevent rushed or spam submission. During the annotation, once workers hover over or click on each annotation, our interface will give them visual feedback, which is more interactive. Once the annotation is completed, workers can review color-coded annotation overview and make modifications easily. Once we had our interfaces ready, we started to post our tasks to Amazon Mechanical Turk. We recruited 800 workers and evenly divided them into 2 groups. 400 workers would work on the basic interface and 400 workers would work on the advanced interface. After that, we divided and posted 200 abstracts into 4 batches, where each batch contains 50 abstracts. For abstracts, we broke down them into small sentences, resulting in 3,177 unique sentence fragments. For each sentence, we collected 20 labels. And we posted all tasks twice because we had 2 different interfaces. The total cost of the Turk data collection was $4,508. And we paid the worker with ethical amount of money that above $10 per hour. To assess label quality and remove underperforming workers, we worked with a biomedical expert and a computer science expert for gold standard data. They are referred as bio-expert and CS expert later. The bio-expert is Dr. Ding, our co-author, and she serves as a faculty member at the University of California, San Francisco's School of Medicine. The CS expert is one of our authors who is a PhD student in informatics. In reality, domain experts are not always available. Some studies asked CS graduate students to label bio-NLP data when the bio-expert was not available. The CS expert in our study was a great alternative for the domain expert, and he can represent as the upper limit for non-expert performance. To simulate the scenario that domain expert was not available, we used CS expert's annotation to assess label quality. At the end of our study, the inter-annotator agreement between 2 experts is 0.788, which is very high. To assess label quality, we set 3 rules and we manually reviewed workers to see if they fell into one of the scenarios. The first rule is label accuracy, which is based on CS expert labels. The second rule is probability agreement between the majority vote and individual workers. If a worker did not agree with the majority for the most of time, we suspect this worker might be underperforming. The third one is the probability of labeling other. The other category should be selected if the sentence does not fall into any other category, which happens rarely. If the other selecting rate is higher than 10%, we would suspect the worker has spammed our annotation. By following these 3 rules and manually reviewing all suspicious workers, we revoked the qualification from workers who were identified as spammed workers. During the latter aggregation, we had 3 cleaning rules. The first rule is called all workers. In this rule, we kept all labels without modification. The second rule, exclude by worker, involved removing labels exclusively from those workers identified as underperforming workers within a specific batch. For instance, if workers in batch 3 are flagged for underperformance, only their labels from batch 3 would be removed, while their labels from previous batches remain aggregated. Consequently, once labeled as underperforming, these workers are precluded from participating in tasks for batch 4. In the third rule, exclude by batch, we removed all labels from any workers identified as underperforming workers. For instance, if a worker is identified as underperforming, all of the labels contributed by this worker across all participated batches will be removed. After we got all workers' annotations, we used 8 different aggregation methods. Let's quickly go over each aggregation methods. Majority vote is based on the most common answer from workers. The David-Skeen method evaluates each worker's level of expertise and leverages this expertise to determine the final answer. The one-coin David-Skeen variant modifies the original method by altering how workers' levels of expertise are aggregated. Gilad estimates the difficulty level of each task and they analyze the final answer. MMS are also assess workers' expertise level and estimate the final answer by resolving a rank 1 matrix completion problem. MACE focuses on determining if a worker is spamming and creates distribution for each worker and calculate the final answer. Due to the lack of detailed information online about Wawa and ZBS, we reached out to the developers at CrowdKit for insights on these algorithms. Wawa offers a modest yet intuitive enhancement over majority vote. ZBS was initially designed to manage streaming response. It can rapidly and effectively update each user's skill for an aggregation result. For GPT-4 annotation, we adopted the full worker instruction from Code-19. In Code-19, each prompt only included each segment for a 0-shot. To ensure GPT-4 had the same access to instruction as the human crowd workers, we crafted a new prompt strategy that encompasses the full abstract for 0-shot processing. We also had 2 temperature settings and we ran each setting 5 times, Then we used majority vote to aggregate the GPT-4 results for each temperature. The total cost was $122.08. After collecting labels from crowd workers and GPT-4, now we present our experimental results. We first conducted a preliminary evaluation by using BioExpert's annotations as gold standard labels. Using all worker cleaning strategy and applying majority vote, workers from basic interface and advanced interface had accuracies of 47.7% and 44.2% respectively. GPT-4 with temperature of 0.2 had higher accuracy compared to temperature equal to 1. It had accuracy of 83.6%. The CS expert had an accuracy of 85.9%, which is the highest among all results. In the bar chart histogram, the accuracy levels of workers using the advanced interface were marginally higher than those of workers using basic interfaces. This suggests that a more user-friendly interface can enhance the accuracy of the individual workers. Then, we experimented with 48 different combinations, which included 2 different worker interfaces, 3 label cleaning methods, and 8 label aggregation algorithms. Both exclude by batch and exclude by worker improved the accuracy of aggregation, but the exclude by worker cleaning algorithm produced superior results. Here, we showcase the best results for basic and advanced worker interfaces under exclude by worker strategy. The figure's x-axis shows the number of workers whose labels were used in the aggregation process. The y-axis shows the accuracy. The highest label aggregation accuracy achieved through the basic interface stands at 67.5%, while the advanced interface reached the best accuracy of 81.5%. Both accuracies are below the accuracy of GPT-4's label, which is represented as the green dashed lines at the top of the figures. From the 48 different aggregation combinations, we found pairing exclude by worker cleaning strategy with the one-coin David Skeen method under advanced interface achieved the best accuracy. However, this best result did not outperform the GPT-4. Despite our considerable efforts to enhance the aggregation accuracy, none of the 48 combinations we tested were able to outperform GPT-4 in terms of accuracy. Given that no purely crowdsourced aggregation pipeline outperformed GPT-4, we speculated on the outcome of treating GPT-4 as one of the crowd workers and merging its labels with those from the crowd. Could this combination exceed the accuracy of GPT-4 alone? By combining GPT-4's labels into the aggregation process, our results show the potential of exceeding GPT-4's solo performance. We showcase 2 best results in 2 figures. The x-axis in each figure indicates the number of human workers in the aggregation. For example, count of 5 refers to a mix of 5 crowd workers and the GPT-4 label. We found one-coin David Skeen and Mace aggregation methods could achieve higher accuracies than GPT-4 solo after adding GPT-4 in the advanced worker interface. They had accuracies of 87.5% and 87% respectively. One-coin, David Skeen, and Mace are the only 2 algorithms out of 8 aggregation algorithms that could surpass solo GPT-4's performance after adding GPT-4's labels. This is only true for labels collected through the advanced worker interface. In another word, out of 48 combinations, only 6 combinations could surpass GPT-4. Our study leads us to several key insights. First, the value of expert-level, extremely high-quality labels will likely increase. Second, future research may shift from using AI to help humans to using humans to improve AI labeling, as we found that GPT-4's accuracy can be further improved by adding a few crowd labels. Finally, we believe the HCI problems in human annotation, such as developing systems and interfaces that allow non-expert annotators to perform reliably, will become centered again. As collecting extremely high-quality and reliable annotations is more critical in the era of large language models. The integration of GPT-4's labeling with crowdsourced inputs significantly enhances performance, exceeding the accuracy of GPT-4 alone. This opens up the possibility for creating intelligent and interactive systems in the near future, where regular users can actively contribute to and refine the capabilities of LLMs. Thanks for watching.